Good morning, CP Calculus class. This is Miss G. It is Thursday, April 16th. I hope you're all doing well. Today, I only have some requested problems to go through. I don't have any new material. You're probably happy about that. So I have 3 problems I'm going to work through. One is number 11, number 15, and number 21 from page 348, yesterday's assignment. So the first one is number 11. They gave you a diagram and with a graph, and the function was y equals 1 over x squared. So we're finding this area between 1 and 2, the curve, the x-axis, and the vertical lines 1 and 2. Ooh, I forgot to mark the x-axis. There we go, x-axis. Okay. So our integral is the integral from 1 to 2 of 1 over x squared dx. Now with this problem, you have to remember how we integrated these using our power rule. So we have to rewrite 1 over x squared as x to the negative 2 power. So now we're looking at the integral from 1 to 2 of x to the negative 2 power dx. Now, we do our process where we add 1 to the exponent, so negative 2 plus 1 is negative 1. We divide the current coefficient, which is 1, by the new exponent, negative 1. And then that's our antiderivative, which simplifies to negative 1 over x. And then we're going to evaluate it from 1 to 2. So first you plug the 2 in, and we get negative 1/2. And we subtract, by the fundamental theorem of calculus, we subtract what we get when we put the lower limit of integration in, which here is 1. And so we're substituting that into negative 1 over x. We get negative 1 over 1. Simplifying that, we get negative 1/2 minus a negative 1, which gives us plus 1. So our answer is 1/2. I hope you followed that. All right, so that's number 11. Now let's take a look at number 15. All right, number 15. Ooh, that looks like a lot of stuff. All right, so let's just look at part of it for right now. So number 15, the function is y equals x squared plus 4 over x. And so we have to write the integral. Here's our diagram. Our function is x squared plus 4 over x, and we put in our dx. Our limits of integration are shown in the diagram along the x-axis from 1 to 4. Those are the boundaries on the x-axis for the shaded region. So from 1 to 4, and there's our function. All right, so this is the type where we had the monomial single term in the denominator. So we split this rational expression into 2 parts. So I split it into x squared over x plus 4 over x dx. From 1 to 4 is our integral. And then I simplify this. So x squared over x is x, and we're going to evaluate that from 1 to 4. And then this 4 over x is the same thing as 4 times 1 over x on dx. And then since 4 is just a coefficient, in the next step, I just pull the 4 in front of the integral sign. Okay, now I'm going to integrate both of these. You could have done it all as the same integral. You didn't need to really... you didn't really need this step where I have this integral and this integral. If you wanted to just all put the x and the plus 4 times 1 over x into the same integral, you could do it. But it's easier, I think, to see as 2 separate ones, especially because we have the 1 over x here. All right, so the antiderivative of x, add 1 to the exponent, we get x squared. Divide the coefficient by the new exponent, we get 1/2. So the antiderivative of x is 1/2 x squared. Evaluating it from 1 to 4, let's look at what's going on over here with our antiderivative. The antiderivative of 1 over x from last chapter is the natural log of the absolute value of x. And we just bring down our 4 coefficient, and we're going to evaluate that from 1 to 4. All right, what does it look like when we evaluate it? Let's see. We substitute 4 in for x first, and then we substitute 1 in, and we're going to subtract. If we just work on that one for a moment, we will have 1/2 of 16, 4 squared, minus 1/2, which gives us 8 minus 1/2. All right, so there's that one done. Now, let's go back and do this one. Substitute in 4. We get 4 ln absolute value of 4. But again, we don't need the absolute values because 4 is positive. Minus Substitute in the 1, 4ln, absolute value of 1, but 1 is positive. Now, if you remember from last chapter that the natural log of 1 is 0, that's good if you remember that. If you didn't remember that, you'll put that in your calculator, get natural log of 1 is 0. So let's simplify this. We get 4 ln 4 minus 4 times ln 1, which is 0. And that simplifies to 4 ln 4. Now, if you got this answer, 8 minus 1/2 plus 4 ln 4, that's correct. I probably would want you to simplify the 8 minus 1/2 to 7.5 plus 4 ln 4. I would accept that. If you put that whole thing in your calculator, you get 13.045 or 13 45 thousandths. And that's correct as well. Some people were a little confused maybe because the answer in the back of the book didn't look like this. The answer in the back of the book looked like 8 ln 2 plus 15 halves. Well, we can see where the 15 halves came from because 8 minus 1/2 is 7.5, and that's 15 halves. But where did the 8 ln 2 come from? Let's take a look at our 4 ln 4. They took the ln 4 and made it ln 2 squared. And then they used the log rule, which can take the exponent and put it in front of the log. And then there's already a 4 there, so you end up multiplying it. So they get 8 ln 2. They were a little crafty there. You don't have to do that. I would certainly accept the other answers. The 13 45 thousandths, even the unsimplified version here, and that would be fine. Okay? Either way, it comes out 13 45 thousandths if you put it in your calculator. All right, so there's that one. I can see why that caused a little bit of confusion with the answer choice, the answer at the end of the book. All right, the next one, I did it 2 different ways, and then I decided that the alternate approach was better. So I'm going to do the alternate approach first. So here was the function. The integral from -1 to 1 of 4 minus 3t quantity squared dt. Yeah, I don't like when they use t's either. They get confused with the plus signs. So if you don't like the t's in the problem, you can change them to x's. I'm okay with that. But since this exponent is only a 2, not a 7 or a 10 or something where we wouldn't be able to FOIL this out very easily, we are going to just FOIL that. Multiply 4 minus 3t times 4 minus 3t dt, and then integrate it from -1 to 1. So if I multiply this out, I get 16 minus 12t gives me minus 24t, and then plus 9t squared dt, integrating from -1 to 1. So now we find the antiderivatives. You don't have to split them into 3 integrals. You can just do them as one polynomial expression here. So the antiderivative of 16 is 16t. The antiderivative of 24t, if we add 1 to the exponent, we get 2. Divide 24 by 2, we get 12. So we get 16t minus 12t squared. Add 1 to the exponent on this t, we get t cubed. Divide 9 by the new exponent 3, we get 3. So here's our antiderivative, 16t minus 12t squared plus 3t cubed. We're going to evaluate it from -1 to 1. First, I plug the upper limit in. So I'm going to plug 1 in everywhere I have a t. Then I'm going to plug in -1 everywhere I have a t. And I'm going to subtract. So I'll simplify this. You can see that's going to be 16 minus 12 plus 3, which turns out to be 7. I'll simplify this. This is -16 minus 12 minus 3, which simplifies to -31. And 7 minus -31 is 38, because it's 7 plus 31. There we go. I'll show you the other way, but I think when this is just a squared, it's just as easy to FOIL the problem out and find the antiderivative. But if that's not a squared, then you wouldn't want to multiply this whole thing out if it's a higher exponent. So the alternate approach would be to use the u to u substitution. So I'll show it here. 4 minus 3t is my u. Derivative of that is -3 dt. There is no negative 3 in front of my expression here. So I picked up a negative 3 I don't want. So I put a negative 1/3, the reciprocal of that, a negative 1/3 in front of my integral. And now I do my substitution. I'm integrating u squared du. And I didn't put any limits of integration, as I explained yesterday. When you have u's, the limits are not ones. So I'm going to wait until or not the original limits. I'm going to wait until I put the t's back in at the end and then put these limits back in. So now I find the antiderivative of u squared. I know you all know that's 1/3 u cubed times the negative 1/3 out front is negative 1/9 u cubed. Now I'll put the 4 minus 3t back in for the u. And now I'll put the original limits of integration back in my problem. From negative 1 to 1 is where we're going to evaluate it. But according to the fundamental theorem of calculus, we always plug in the upper limit first. So I'm plugging a 1 in for t here and a negative 1 in for t here. And then I just have to work this out. You can do it on your calculator. You can use PEMDAS, please excuse my dear Aunt Sally, to work this out. You multiply the 3 times 1, and then you subtract it from the 4, you get 1. And over here, this is going to turn out to be 7 cubed. If you do that, all that math out, arithmetic actually, you'll get negative 1/9 plus 343 ninths, which is 342 ninths, which is 38. Same answer as before. Okay? Just wanted to show you that, but you could use the other method, and I'm fine with that. Okay, so I don't have a new assignment today. I mean, I don't have a new topic, but I do have a few more of these problems to practice to make sure that you understand it. It's page 348, numbers 12, 18, 20, and 22. Because these are the even ones, I did post the answers here. Answer to number 12 is 4. Number 18 is 135 over 2, or 67.5 if you prefer. Number 20, the answer is 10. And 22 is 4 2/3, or 4 667 thousandths, 4.667. All right? I hope you followed all that, and I hope you have a great day. Take care.